Hello, everybody. Thank you for joining this technical webinar. Can everybody please disable the sounds and the pop-up notification by simply going to the cog symbol in the bottom right corner of the screen and switching on, go to the notification settings and untick all the boxes, please. Our topic today will be grid-friendly photovoltaic systems, and this will be presented by Dr. Hosian. And I'll run you guys through the commonly asked questions, which is everybody registered for this webinar will receive both a copy of the PDF slides and the link of the video within the next 2 business days via email. Certificate of attendancy. This will be provided to you, to all the attendancy for a live attendancy for a technical topic webinar. This will be a link and a QR code to a short form survey provided at the end of this session, which you need to complete in order to receive one. So you can only be receiving the certificate of attendancy once you go to the link or the QR code and completing the short form. Please kindly do that at the end of this technical webinar. This is a brief introduction about EIT for those who are joining for the first time. We are one of the only institutions in the world specializing in engineering. We currently offer a range of industrial focused courses, mainly across civil, mechanical, electrical, industrial automation engineering, from short courses all the way through to a Doctor of Engineering degree. All our courses are offered both online and on campus for certain courses, which means students can study from wherever they are in the world, but also experience studying engineering in Australia if they want to. All our vocational programs plus higher certificate education degrees are recognized and accredited by the Australian government, but also have a number of courses internationally recognized under one of the 3 international accords: Sydney, Dublin, and Washington. And from here on, I'll leave Dr. Hossein to take you guys through the whole presentation. Thank you, guys.
Thank you very much. Thank you very much, everyone, for joining the session. So the agenda for today, I will be starting with high penetration of renewable energy systems. So we will be talking a little about some of the new standards and regulations in this area. And I will continue with the principles of what we call as flexible power point tracking, and especially under partial shading conditions. And then we will use this feature in photovoltaic systems to provide power system frequency support. And at the end of the session, I will be talking on a different topic a little, which is modeling of renewable energy systems for power system studies. I'm currently a research fellow at the University of Western Australia, and we are working with a company called Magellan Power on a design of 1 megawatt energy storage system. Previously, I was a senior research associate at the University of New South Wales, and Before, I was a research fellow at Nanyang Technological University. I I got my PhD in Singapore at the Nanyang Technological University and both my master and bachelor degrees in Iran from Amir Kabir University of Technology. Okay, regarding the high penetration of renewable energy resources, as everybody is aware, every day and every year, the amount of integrated energy, renewable energy resources is increasing, especially in this figure you see in the screen. You can see the high penetration of photovoltaic systems that are increasing in the power system. But not only this high penetration of renewable energy resources have its own benefits to the system, it also makes some new challenges. One of the first challenges is that these systems are dependent on the environmental conditions. Let's talk mainly about photovoltaic systems, and especially now that is winter in Australia, every day based on the whether it's a cloudy day, etc. The output power of this big photovoltaic system is changing. So their output power is dependent on the environmental conditions. Another challenge that they make to the grid is leading the grid to be low inertia. What does that mean? Before, before in the conventional power system, we were having mainly synchronous generators that they have an inherent inertia with them. And this inherent inertia helps to stabilize the grid under transients. But now that most of the uh, uh, conventional generators are getting replaced with what we call inverter based or renewable energy based systems, that inherent inertia is getting reduced and systems are experiencing low inertia. Another challenge is lack of visibility to power system operators. Again, before, most of the power systems, most of the generators were directly managed with the power system operators. But now, especially nowadays, you see a lot of photovoltaic inverters are installed inside houses, and the power system operators do not have direct access to control of these inverters. And another thing is that there is not only about controlling them, it's also about lack of visibility of operation that these systems have. Okay, and then as I mentioned, is it goes to lack of central control. That because this because these renewable energy resources are not directly managed with the power system operators, there is lack of central control. Just give me a second. It seems my notifications are on, and for some reason, okay, I suppose now should be better. Okay, so now I'm gonna talk about a little about new standards and regulations that are imposed by new grid operators. One of the very big in one of the this new requirements is what we call as frequency support. In frequency support, as you can see in the figure, which is an example. Now you can see is I have around this for four different countries: Australia, South Africa, Germany, and Denmark. The main idea is you can see if the frequency of the grid is within a nominal range, the system or the photovoltaic system should keep some amount of power reserve in it. And if the frequency drops below that nominal range, as you can see here, the output power of the system should increase towards the maximum available power. So, and in this way, the amount of power reserve which is available in the photovoltaic system can help the power system or can support the power system under frequency disturbances. On the other side, you can see if the frequency increases, there is a requirement of reducing the power from these photovoltaic systems. And again, the idea is to support the grid under frequency increase conditions. The other requirement that we have is called as voltage support. For the voltage support, we are looking at the voltage of the point of common coupling that each PV inverter is connected. Again, as you can see in this area or in this range, if the voltage is within the nominal range, there is no requirement of injecting any amount of reactive power to the grid. However, if the voltage of the point of common coupling increases or decreases outside the nominal range, the PV inverter is required to either inject or consume some amount of reactive power. And again, as you know, injecting or consuming reactive power helps to bring the voltage or helps to bring the voltage close to the nominal range. So that's another way that a photovoltaic system can support the grid under these conditions. And of course, we are going to have different types of requirements. Here there is a summary of some of these requirements. In some of the conditions, as I explained now, the system is required to keep some amount of reserve power in the system to be available under grid transients, either voltage or frequency. Another requirement you can see here in zone 3, which what we call as power ramp rate, and standards are imposing this power ramp rate control to photovoltaic inverters or in general renewable based inverters. And the main idea, as you can see here in the figure, if in case due to some reason the output power of the inverter wants to change rapidly, we need to limit this rapid change, and we need to limit the output limit the change of the output power to a specific value. This happens when the inverter gets on, or for example, if during the day there is a cloudy day and the shade is moving away and the output power wants to increase. Another requirement, what is it called, what we call usually is power limiting control, or some people call as constant power control. And This requirement is the limit that is set by grid operators. This limit can change based on time of the day, and that's the maximum limit that the inverter should inject to the grid. And sometimes this maximum limit is just limited by the inverter rating itself, because as you know, usually in the photovoltaic systems we oversize the installed PV panels, and that means, and that's even an economical number, by 10 or 20, 10 or 15%, we increase the size of or the rating of PV panels that we installed compared to the inverter rating. And if by chance the output power or the available power from the PV panels are higher than the rating of the inverter, the power is limited to this condition. So all of these different requirements that we mentioned, they impose an active or a regulated power in the output of the inverter. So that means, unlike the conventional solutions that we just inject the maximum power to the grid from the photovoltaic systems, now we need to move to a new operating condition, which we call as flexible power point tracking. And as is obvious from the name, again, is unlike the maximum power point tracking solutions available in the literature, we do not just inject any amount of power which is available to the grid blindly. However, we always look at the grid condition, and based on the grid condition, we adjust the output power. A basic principle of the flexible power point tracking, or what I will be calling from now on as FPPT, is shown in this figure. You can see that the operating point, instead of being at maximum power point, needs to be shifted either to the left side or right side of the maximum power point, and the operation point now is imposed by the power reference, which this power reference can come based on any of the requirements that I have discussed. It can be from the power limiting control, it can be a limit that is set due to the power ramp rate control or power reserve control. So the idea or the basic principle is, now in a photovoltaic system we have a power reference, and we need to follow this power reference, and that means the output power of the system needs to be regulated to this power reference. And the idea is, or the question is, how do we track this power reference? And that's the basic principle of flexible power point tracking. Here, one of the very simplest flexible power point, or the algorithm, one of the simplest algorithms for FPPT is shown. You can see we are having two different steps in the algorithm. The first step is the calculation of the voltage step, because our algorithm is based on the perturb and observe. Of course, it is a modified version of the perturb and observe algorithm, but the first part of it is to calculate the voltage step that we need to consider for perturbation. And calculation of the voltage step also depends on the operating point of the system, whether the system is in the steady state or in the transient, and whether the grid is in the steady state or no. So there is a flow chart. I am not gonna go through the details, but the main idea, as I mentioned, is to calculate the optimum voltage step for this perturbation. And the second stage is, of course, to calculate the voltage reference. And again, we have developed very simple approach based on the perturb and observe, and based on the side of the operation that we decide, uh, we would like to operate whether we would like to operate in the right side of the maximum power point or left side of the maximum power point. We can adapt the algorithm, and the algorithm, as you can see, it just sees the delta P to delta V, and it also considers whether the power reference, whether the available, whether the current output power of the inverter is larger or smaller than the reference, and then it makes a decision on how to which direction to move the voltage. Of course, we tested and validated this through experimental validations. A photo of a setup is shown here. We have a DC-DC converter, and we were using, of course, DS space for implementing the controller, and a photovoltaic emulator to emulate the photovoltaic curve. We tested under different operating conditions. On this case that you can see, the irradiance of the PV curve has been changed from the blue curve to the green curve, and you can see, because the operation point was set to be on the right side, slowly that the irradiance changes, the operating point moves from B to point A. And at the very beginning, the operating point was set to be the maximum power point, and then it moved to point B, which is following the power reference that was set by the by the converter. Okay, so the main remarks that we have, of course, the algorithm is able to operate for both maximum power point and flexible power point. So if we want to operate the algorithm for maximum power point, we just need to set the power reference to be larger than the available power. The proposed solution is flexible to operate in both right and left side of the maximum power point, and accordingly, it can be applicable for both single and two-stage photovoltaic systems. We can obtain fast dynamic response, as I mentioned, by proper selection or optimum selection of the voltage step, as well as low power oscillations, again by optimum selection or adaptive selection of the voltage step. Now we would like to talk a little more in details on how can we achieve FPPT under partial shading conditions. You can see, once the system or the irradiance is a uniform irradiance, the operating point or the finding of the operating point was pretty simple, because with some simple perturbations we were able to adjust the power to the reference. However, once we have partial shading conditions, first of all, we are having multiple peaks in the PV curve, and another challenge that we get is what we call as intersection points, that they have somehow infinite derivation of the delta P to delta V. And on the other side, we are having multiple operating points for a single power reference. So the idea is how we can regulate the power to the reference with a fast response. So there is a quite complicated solution for this aim, but I'm just going to give some of the basic principles of this solution. For example, one of the very simple solutions, if you would like to reduce the power, let's say if the operating point is at point 1 or point 1 here, and the power reference is smaller than the current power of the V, so we need to reduce. But we need to reduce the power. But then the question is, how do we reduce the power? On which direction we move the voltage in such a way that we do not get stuck on this area between the intersection point and a local maximum power point. This is one of the challenges. And to solve this, we can define, or we can decide on the operation point based on the moment that the power reference gets smaller than the output power. The other operating condition is, of course, again, if we need to increase the power. So in this case, it really depends on the current operating point. For example, if by chance the current operating point of the system is in the same area or in the same local maximum power point as the point that we get the power reference, it is just simply using a perturb and observe to increase the power. However, if, let's say in this example, the current operation point of the system is in different local or in different area than the area corresponding to the power reference, like what you see here. Again, we always want to first check the local maximum power point, because the first local maximum power point may give us a solution. We don't want just to always reset the algorithm to the very beginning of the curve. And this is one of the principles that we are considering. So we always first check the local maximum power point. If it does not satisfy, then we need to start scanning the curve. Again, this is another case if the power reference is larger than the global maximum power point, in which we need to obtain a global maximum power point tracking solution to bring the operating point to the GMPP. But again, deciding on when we need to choose a global maximum power point, or when we need to choose the local maximum power point, or when we need to choose to reduce the voltage or increase the voltage, requires considering different operating point, which will end up to a quite sophisticated algorithm, as you can see here. And we also needed to modify what we call as what was called as GMPP, one of the GMPP solutions. We needed to modify that solution to adapt it to our algorithm and use that solution in such a way that we can regulate the power to the reference set by the grid operator or one of the standard requirements as I discussed before. Again, we have tested the solution or tested the algorithm with experimentally, and you can see on this example, for example, the irradiance condition has changed from the blue curve to the green curve, and as you can see, the operating point has moved to the correct point in a fast manner, and we did not need to scan the whole curve to find the correct operating point. Another example you can see here that the irradiance has changed from curve 3 in the figure, the purple curve, to the curve 4 or IR4 or the red curve. In this specific condition, you can see the power reference is larger than the GMPP of the new curve, and the algorithm was required to find and detect that it needs to find the global maximum power point, and it needed to move the operating point to that point, to the GMPP. Okay, so now we would like to see the application of flexible power point tracking on frequency support. So we do not want to just implement the flexible power point tracking, and in this part we are looking to see how FPPT can support the power system on their frequency transients. You can see a very normal or very frequent frequency disturbance that normally happens in the power system. This specific disturbance can happen because of the load step change or a fault in the grid. As you can see, the frequency has dropped. So in this case, the power system or photovoltaic system can operate or can be controlled in 3 different ways, as shown in the lower part of the figure. One way is like the conventional solutions, that it just follows the maximum power point. And as you can see in this blue curve, the system or the photovoltaic system does not really care what has happened to the grid. It just continues to generate or extract the maximum power to the grid. This is a conventional solution. However, what we are proposing, and we discussed before, is to keep some amount of power reserve in the system during the steady state and try to use this available power reserve during the disturbance. You can see, for example, in the second solution, which is this green line or green curve, there was some amount of power reserve before the transient, and since the frequency has dropped, the output power of the PV system has increased, and accordingly, once the frequency is increased back to the nominal, you can see that the power also is reduced back to keep that amount of power reserve. Of course, this solution is better than maximum power point solution because in a short period of time, the system or the PV system is supporting the grid under this frequency disturbance. However, there is still a challenge in this second solution, which was the green line. And that challenge is during the period that the frequency is increasing towards the nominal, the synchronous generators not only they need to compensate for the change in the load, they also need to compensate for the reduction of the power that is happening in this area. That means they need to compensate for two facts at the same time, which this phenomenon delays the response of the system. A better solution is what we see in the red curve. You can see the power has been increased to the maximum power, or based on the frequency drop, it has been increased. But instead of just decreasing after the frequency has changed back to the nominal, the PV system stays at that maximum power for a period of time. And after the instant that the frequency has been recovered, the output power of the PV system is decreasing and it is following a ramp rate. So in this way, firstly, during the disturbance, the generators do not need to compensate for both the reduction of the PV as well as the load. And secondly, the reduction in the PV power has been occurred following the ramp rate. And that means the second transient that happens here is so slow and so small. And that means the frequency, it does not affect the frequency of the grid too much because the generators are able to compensate for the power change. So this is how we implement the solution. We define different group loops, and based on the operating point and based on the frequency of the grid, we can calculate the corresponding power reference. But the idea or the basic idea is as I mentioned in the previous slide. We implemented this frequency support on a photovoltaic system. As you can see, the output here is the power reference, and this power reference is fed to what we call as flexible power point tracking to calculate the voltage reference for the PV system. We try to test this on a system close to real, and to do that we implemented a composite load model. As you might be aware of, recently in USA they are introducing this composite load model, which is an aggregated model of a distribution feeder. So to be very clear, this model that you see on the screen is not a model of one house. It is a model of an aggregated model of a distribution feeder with a lot of houses, industry premises, etc. And in this composite load model, instead of just like conventional solutions that we put a zip load, we are simulating different types of loads. For example, different types of motors that are, some of them are high inertia motors with constant torque, like motor A, and etc. We also simulate the electronic loads and static loads. But one part of this model is the photovoltaic systems or the DG systems. And now we try to implement the proposed solution and the proposed behavior in this model and see how the power reserve and the flexible power point tracking can enhance the frequency of the grid. These are specifications of different types of load, which I'm not going to go to the details. But what I would like to show here in this slide is that once we follow that the proposed solution, which if you remember it was a red curve that I showed at one of the slides before, you can see the frequency nadir or the minimum frequency under the disturbance has been improved. And this is how the PV system is able to support the grid under this condition in real applications. Okay, so now I'm reaching the last part of the presentation for today, which is a modeling of PV inverters or renewable energy-based inverters. What do we mean? First of all, what do we mean with modeling and why even the modeling is important? Let's look at a real example that has happened in Australia. There was a separation event. The transmission line has gotten faulty between Queensland and South Australia in 2016, and that was one of the big events in the NEM or National Electric Market in Australia. You can see after that specific time of the event, which was during the noon time, especially during the noon time, which a lot of power was produced by the PV inverters. You can see after the event, after that fault in the transmission line, the frequency in the Queensland has been increased from 50 to around 51 Hertz, and the frequency in New South Wales, Tasmania, and South Australia has been decreased to almost 49 Hertz. You can see here and here. Okay, so this is an event that has happened in the system. But what we are interested is to know how the PV inverters performed during such an event. What we see based on the data, collected data on the network, we see that, for example, in Queensland, that there was an overfrequency and the PV inverters were supposed to decrease their output power. We do not see enough reduction in the output power based on the standard. That means, for example, we were expecting that the curve is gonna go drop to somewhere like this, but it did not drop to that point. And that means even all the inverters that are installed are certified by the standard, they did not perform correctly under this condition. So now the aim is we would like to model and we would like to know the behavior of the power system which has high integration of PV inverters, and we would like to have an aggregated model of these PV inverters that we can do power system stability and other studies, and then we can determine how much reserve we need to keep in the power system. To do that, we needed to obtain this model. We need to have, or we need to test a high variety of photovoltaic or the commercial photovoltaic inverters. We did test more than 35 commercial inverters that they were rated between 4 to 10 kilowatt. We needed to make a benchmarking setup which has a grid emulator and a PV emulator to make consistent tests. And here in this specific case, you can see that the inverter under test, which is here, you can see is a PV inverter, one of the commercial PV inverters. We need to impose this inverter to different kinds of disturbances and record the data. Based on the recorded data, we calculate an aggregated model for these PV inverters. So I'm going to show only two types of tests as an example. We have done more than 100 tests on each inverter, but I'm just showing two types of them, two sets of tests. One of these tests is testing the inverter for voltage sag. First of all, we look at the standard requirement, and we see that the corresponding standard in Australia, which was AS4777, it mentions that if the voltage of the grid is smaller than 180 volt. By the way, here in Australia, as you know, the voltage or the nominal voltage is 230 volt. So if there is a voltage sag, the inverter should not disconnect for a period of 1 second, but it's not clearly mentioning what does the inverter should do. The only test that a standard performs, it just ensures that the inverter did not disconnect and the circuit breakers or the contactors are yet connected. So now we are making voltage sags conditions and with a duration less than 1 second, and we test different types of inverters from different brands, and we want to see how do they perform. So this is a voltage profile that we impose to the inverter. We reduce the voltage from 1 per unit to almost 0.2 per unit, and the duration of this voltage sag varies. Sometimes we put 80 millisecond, 100 millisecond, and 200 millisecond. So the inverter 1 under this type of voltage sag, you can see it has decreased the output current to almost 0, which is this red line in this figure. And you can see after the disturbance has been recovered, which is the blue curve on the top subfigure, the inverter has recovered to its nominal current or the current before the fault. However, we see another inverter, I mean here we call it as inverter 2. Under the similar test, you can see it is injecting some amount of current, and you can see a clear difference in the performance of these two inverters, and both of them, to be clear, are following the standard. None of them has disconnected. The third example is this inverter 3 that under the similar condition, you can see it shows high currents, and after that the inverter becomes unstable, but still it did not disconnect. You can see there is some amount of current injected to the grid. Even this inverter is following the standard, is certified under the standard. But now you could clearly see three different types of performances. And as I mentioned at the beginning, Now we would like to know, now that we have so many of these inverters installed in the grid, how are they going to behave if such a voltage sag exists? And then we can plan for for reserves and other supports to make sure our system stays reliable under these conditions. Another set of tests is the operation of these inverters on the phase angle jump. You can see for the phase angle jump, uh, as you might be aware of, the angle of the voltage changes suddenly. This phenomena can happen because of um, disconnecting or connecting a transmission line, or even a transformer, or a fault in the system. It's an frequent phenomena that happens in different power systems. Now we would like to simply see what does the inverter do under these conditions. You can see the inverter 1, which rides through the voltage angle jump. You can see the inverter, there are 1 or 2 cycles that the inverter gets a little out of phase, but it regulates the power back to the pre-fault condition. Here you see another set of inverter that fully disconnects. You can see here the current output becomes suddenly 0. So you can see again clearly we have 2 types of inverters from 2 different brands, and they show completely different behaviors on a similar phase angle jump. And again, the aim is, how are these inverters going to behave as an aggregated model under such conditions? And as I mentioned, again, the aim here is we would like to find the model, or define a model for DG in this composite load model. Just an overview of this composite load model, which is a quite complicated model with different sets of parameters. And this is why we need to implement and test the inverters based on the percentage that they are installed in the grid, uh, based on each grid or each part of the grid even. We need to tune the parameters of this composite load model and aggregate it with the rest of the system. So finally, as a summary, I have mentioned several challenges that can happen in the power system because of the high penetration of photovoltaic systems. We discussed some of the principles of FPPT, or flexible power point tracking, and we saw the application of the flexible power point tracking in grid frequency support. And at the end, we have seen some of the different behaviors of the inverters under grid transients, and why it is important to provide an aggregated model of these inverters. That's the end of my presentation. So if there are questions, I can answer, and otherwise we can end the presentation.
Thank you, Dr. Hussein, for that lovely presentation.
No worries. Thank you very much.
Um, Okay, please look out for our upcoming webinars, which the first is on an insight into Australian engineering jobs and Engineering Australia membership, which will cover various insight on studying engineering in Australia, Australian engineering jobs of the future, and starting a career in engineering, and which is going to be happening on the 24th of August, and also hydrogen production storage application for sustainable future, which is the next webinar, which is also basically happening on the same day, just after the first webinar. And this will cover technological pathways for generating hydrogen, technologies that store and distribute hydrogen from the point of generation to the end use, applications of hydrogen. Next, I'll be running you through the upcoming EIT courses. As you can see, most of them are starting in February, the 13th of February, 2023. Bachelor's of Science degrees, graduate certificate, Masters of Engineering degrees, and Doctors of Engineering, and more. And there's still also new courses which are going to be coming up soon, and everybody will be introduced to them. Certificate of Attendancy. To receive your digital certificate of attendancy for participating in this webinar, please fill out the form and survey. As you can see your QR code and the scanner. I'll put this on the group, on the chat. Please fill in the survey to receive your certificates of attendancy. And this is the only way you can actually receive it if you complete the survey. I'll leave this for a while so that you can go through it or scan it.
Okay, can I answer some of the questions in the meanwhile?
Yes, Dr. Hussein. Yes, your Q&A actually. Anybody
Yeah.
that has questions can please ask, and Dr. Hussein will be answering any questions.
Okay, so I see some of the, maybe I have missed a lot of questions, but I see one question: how are the generator going to behave during power surges, and what impacts does it have on the emulators? I'm not quite sure what do you mean with emulators, but the main point which I was trying to mention during this session was the generators, they have an inherent inertia because they have rotating rotors, rotating parts, and this rotating machine, because of its inherent inertia, helps to stabilize the grid if there is a frequency disturbance. But this inherent inertia does not exist in inverters, and the whole idea is how can we still support the grid with these inverters, either with emulating the inertia or with other solutions that were discussed during the session. Okay, this is about this question. I see another question. Do you have any recent studies surrounding frequency transients during a large transmission fault? Unfortunately, no. I mean, my main expertise is on the power electronic side and control of inverters. That's why I do not see much or read much about the power system transients. Sorry for that. Is there any other question that I have missed? If somebody can again repeat your question, I can answer. Okay, so if no question, then I suppose we will end up the session. Inverter models. Okay, so regarding the inverter models that we tested, of course, we have tested very different types of inverters from different companies like SMA, Fronius, and other companies. But somehow, due to the confidentiality that we have signed with these companies, we are not able to somehow give the data of their inverters out. That's why you see during the presentation, I was mentioning anonymous names, inverter 1 and inverter 2. Again, how do we control the generator governance during power surges? That is very specific to conventional generators or mechanical generators. As I mentioned, to the extent that I am aware of, it is having because of the mechanical mechanical rotor, which is rotating, it has the inherent inertia. But then the governor always looks at the frequency of the system as well as the speed of the rotor, and based on that, it can adjust the steam or whether it's a gas or whatever. So that's a mechanical process that is usually happening, and that's the voltage, or that's how the government can respond to the grid frequency disturbances. I see another question: what's the maximum voltage that inverters can produce? It depends whether the inverter is a single phase or is a three-phase, and again whether the PV system is a single stage or two-stage system. But as you are aware of, in a single phase inverter, the inverter can maximum produce a voltage which is similar to the what we call DC link voltage, and in a three-phase inverter this value is half of a DC link voltage, and this is because of the topology and because how much each leg of the inverter, what's the maximum that each leg of the inverter can produce. Of course, there are currently, as I mentioned, even one of the events I mentioned. First I mentioned the question: do you foresee significant issues of frequency response in Australia once the large coal-fired generators are shut down? This is why there are a lot of foreseen issues. That's why now AMO and other power system operators are looking for the solutions, and there are a lot of discussions whether only energy storage will solve the issue, whether they need to install condensers, etc. So of course issues exist because the inertia is getting lower and lower, but there are several solutions, and that's what Australian energy market operator and other corresponding companies are investigating the solutions. I see another question here. What are the difference? What are the difference between off-grid generator and on-grid generator? Again, if the question is about the inverter, it is the control is fully different. In a grid connected inverter, we do what we call as grid following control. That means we assume there is a voltage in the grid and we inject power or current to the grid. But while we are in off-grid situation, the inverter needs to make the grid, which what we call as grid former, and that's the controller is fully different. But if you are really meaning about being the generator, being off-grid or on-grid, again, a similar situation exists. If there is an off-grid system that only there is one inverter, there is one generator, then the generator is just making the voltage for the whole system. But while it becomes on-grid, it needs to control the voltage of common coupling based on the power reference and the voltage reference that it gets from the power system operator. Uh, question: when it comes to brands, which brand would you recommend if an individual wants to purchase an inverter? I'm not a purchasing or salesperson. It's what we were testing. It was testing inverters against transients, and it doesn't matter. I mean, sometimes we saw the inverters that are well branded or well-known brands. They behave worse than the inverters that are not branded. But again, this doesn't mean they are not reliable. We were just testing under very specific testing conditions. All of those inverters were following the standard, were complying with the standard. So that's what I'm trying to make it very clear. We were testing under very specific testing conditions, and the aim was to find the operation of these systems or these inverters on the transients.
Sorry to
There's a
cut you,
question.
Dr. Hussein. I think
Yeah.
we've passed our time.
No worries. So we can
We'll
stop.
take one more
Yeah.
question. And okay.
Our
Thank you,
key phase here.
everybody. If you have
Yeah.
any
No worries.
more questions,
Yep.
sorry about that, Dr. Hussein.
No worries. You can continue.
For those who have more questions, please email us at www.eit. No, that's actually our website. Please email us at our webinar at eit.edu.au if you have any more questions to ask, and we'll attend to them. Let me put this in the chat. And please note that the certificate of attendance will be given to you as soon as you're done. When you're done with the survey, within four to 2 days, and also the slides and the PDF also will be given to all the attendee. So that is sorted. Within 2 days, it'll be given to you. So thank you very much, everybody. And for any questions, please email webinars@eit.edu.au. I'll put this in the chat just now. Thank you very much, everybody. Enjoy the rest of your day. If it's an evening, please do enjoy that. And thank you very much, everybody. Thank you,
Thank you very
Dr.
much.
Hussein, for that
Have a good.
presentation. That was lovely.
Thank you very much. Have a
Thank
good
you.
end of the day. Thank you very much. Bye.
Bye bye.
Bye.